we're going to take a look at the two major types of chemical bonds that we'll focus on in Chem 2A and Chem 22. And those two major types of bonds are ionic bonds and covalent bonds. You can see that ionic bonds are found in ionic compounds, while covalent bonds are found holding atoms together in what we can call either a molecular or a covalent compound. So the reason compounds fall into one or the other of these types of categories is based on the type of chemical bond that they have. And you can look at a chemical formula and immediately predict what kind of bond you would expect to find in that compound. So chemical formulas list the number and types of atoms that are present in the substance. And looking at several chemical formulas, most of them you're already familiar with, right? You can see that if I wrote the formula in red, I'm trying to signal that the type of bond present in that formula would be ionic bonding. So sodium chloride, barium fluoride, you would consider these to be ionic compounds having ionic bonding. And the flag is that you see a metal and a non-metal together in the formula. So that's very important. When you look at an ionic compound and recognize that it has a metal plus a non-metal in its formula, then you know that this is an ionic compound and it contains ionic bonding. Looking at the last two formulas that I've written here, water, H2O, and carbon dioxide, CO2. Now you look at the elements that are present in that formula, hydrogen, oxygen, carbon. You look at the periodic table, you know that metals fall to the left of the stair-step line, and non-metals fall to the right of the stair-step line. So oxygen and carbon are clearly non-metals. And remember that situation with hydrogen, although you see it at the very top left of the periodic table to the left of the stair-step line, it is considered to be a non-metal. That's the exception to the left. So hydrogen, oxygen, carbon, all of these are non-metal atoms. Therefore, as soon as you look at the chemical formula and recognize that there are only non-metals present in the formula, then you know that the bonding that is present in that substance, in that compound, is covalent bonding. So, covalent bonds, formula, non-metals only. So let's take a closer look at what's happening with ionic bonding. So I have here on the board, and this is found in Chem 2A, section 6.1, Chem 22, section 10.3. Ionic bonding, what is it? Right? Key words here, 3 key words. Electrostatic forces of attraction. Now we've talked about that before. It's a big fancy term that basically says that positive charge and negative charge attract each other. They want to come close and stick together. So ionic bonding, all bonding, involves forces of attraction between opposite charge, between electrons, which are negatively charged, and the protons that are present in the nucleus attracting those electrons. So ionic bonding, electrostatic forces of attraction that hold metal cations and non-metal anions. So cations positively charged, anions negatively charged, and they're going to attract each other and hold together to form an ionic compound. So here's where we're picking up the metal, the presence of the metal cation and the non-metal anion present in the formula. So coming up here, we know the sodium is positively charged, the chlorine, called chloride, negatively charged, and that's what's causing these oppositely charged ions to stick together. So let's take a closer look at the most common ionic compound that you are familiar with at this point, which is sodium chloride, table salt. So how can we explain why it is that sodium chloride forms from sodium atom and chlorine atoms neutrally? So we're trying to illustrate what's going on. Of course, we know that if we're looking at a neutral atom, its charge is 0, right? So chlorine, neutral, its charge is 0. Why is it that they react together to form the compound sodium chloride? Well, let's put a diagram up here to help us understand that. Okay, so reaching back to Unit 1, electron configurations that you've just been studying. If I asked you to write the noble gas abbreviated electron configuration for sodium, right, looking at the periodic table, you should be able to quickly read from the periodic table that sodium has an abbreviated configuration of neon 3s1. So it has a core configuration like that of neon, and then one electron present in an s orbital in the third energy level. So it has one valence electron, and using the Lewis dot structures that we just talked about, I'm going to show sodium with that one valence electron. Likewise, chlorine, also a period 3 element, but found all the way down towards the right in the halogen family. So it is in family 7A. It has 7 valence electrons, so I show 7 X's around chlorine, and writing its noble gas abbreviated configuration, I have neon 3s2, 3p5. But we just talked about the octet rule. Neither one of these neutral atoms is in its most stable preferred state according to the octet rule. Each one of them would like to have 8 valence electrons, and neither one of them does. So how can they achieve that? Well, it certainly makes sense for sodium, since it only has one valence electron, not a lot of valence electrons, very few, in this instance 1. It certainly makes sense for it to lose or give up that one valence electron, and then it would fall back to having an octet in its second energy level. In other words, it would have a configuration like that of neon. Now chlorine, on the other hand, has 7 valence electrons. It's so close to having an octet. It's not interested in losing electrons like a metal, like sodium is. It's so close to having an octet, it would much prefer, or it reacts readily, to gain 1 electron and then achieve an octet in its third energy level. So you can see that if a sodium atom meets up with a chlorine atom, they're very interested in doing business with each other, to speak in human terms here. Sodium can readily lose an electron and transfer that to the chlorine atom, and that's exactly what happens. Electron transfer takes place, so 1 electron transfer occurs, and then what do we have on the product side? Well, sodium is no longer a neutral atom. It now has 1 less electron, because it lost it, than it has protons in its nucleus, so we're going to indicate in that upper right-hand corner that it now is positively charged. If no number is written, it's understood to be 1. So sodium is now a +1 cation, and it has 8 valence electrons in its core energy level below the second, like that of neon. But by convention, we don't show those 8 valence electrons. We just understand that they're there, that sodium emptied out what was its valence energy level, the third, and now has an octet in the second energy level directly below, and is a +1 cation. Now what's happening with chlorine? Well, it has now its 7 valence electrons that it started with, but it acquired sodium's valence electron. So we're indicating here that it now has an extra electron in addition to what it started with. So it has 1 more electron than it has protons, and the chlorine is now a negatively charged ion. If no number is written, it's understood to be 1. So chlorine, negatively charged, and when it acquires that negative charge, its name changes and it's now called the chloride ion. So each of these atoms has now satisfied the octet rule. Sodium, now 8 valence electrons in its core energy level. Chlorine, we can write here neon, 3s2, 3p6, which is the exact same electron configuration as argon. So chloride has achieved an octet in its valence energy level. Now, once this transaction takes place, what happens? Do these two newly formed ions say, "It's been great doing business with you. You got what you wanted, I got what I wanted. We'll see each other somewhere down the road"? Of course not, because now they are oppositely charged ions. And what do we know about oppositely charged ions? They attract, they stick together, right? So the sodium ions and the chloride ions are now held together by electrostatic forces of attraction. And that is the ionic bond. So ionic bonds are hard to draw because they're invisible forces of attraction. What I tend to do here to emphasize this is just, highlight this unseen force. It's an electrostatic force of attraction that holds the sodium ion and the chloride ion together as a compound. So here is the ionic bond, right? The ionic bond. This electrostatic force of attraction that's operating to hold these oppositely charged ions together. But it's actually more complex even than my picture on the board is able to draw. If you take a look at sodium chloride, and I'm holding up a well-worn model of sodium chloride for you to take a look at, you notice that it doesn't consist of just a single sodium cation and a single chloride anion. In fact, sodium chloride is a huge 3-dimensional array. And that's what I'm holding up here to illustrate a model showing that. In order to appreciate the model, let me give you a color decoding chart here. The green balls represent the chloride ions. The silver represent the sodium ions. And notice, and we won't go into this at this point, that once atoms become ions, changes happen in their size. Right? So chlorine is smaller than sodium as a neutral atom, but once you form these oppositely charged ions, the chloride increases in size and the sodium ion decreases in size because it lost its 3rd energy level electron. So that's a minor point. I will not be focusing on that, testing you on that here in this class, but I do want to point out, if you're looking at this model and puzzled why the difference in sizes compared to the neutral atoms, it's just as I explained. So here is chloride, and notice in this 3-dimensional array what it's surrounded by. So here's the chloride ion, And here's a sodium ion, sodium ion, sodium ion, sodium ion, all surrounding it. And three-dimensionally, there's a sodium ion directly behind it. And if we expanded out the array, there'd be a sodium ion here in front. And likewise, the same situation applies to the sodium ions themselves. So hopefully you're seeing here at the very center of this array, I'm pointing to a sodium ion and what is surrounding it on all sides. What's nearest to it and surrounding it on all sides are chloride anions. So ionic compounds are in fact huge three-dimensional arrays. And we can write that here. They are 3D arrays. And if that's the case, then a good question to ask is, well, why do we write the formula of sodium chloride as NaCl? Why do we write that formula that way if it's in fact this huge aggregate of oppositely charged ions? The reason that we write the formula for sodium chloride NaCl is that it's the simplest whole number ratio of the ions that are present in the compound. So if you took this array and you busted it all apart and you counted how many sodium ions do I have, and you counted how many chloride ions do I have, you'd find that you have equal numbers of each. The ratio is 1 to 1. So all empirical formulas are simplest whole number ratios of the ions in a compound. All ionic compound formulas are empirical formulas. So we'll write that here as well. Empirical formula. And that is the simplest whole number ratio. Simplest whole number ratio of the ions that are present in the compound.